Welcome to my second course, Feedback Amplifier Analysis, the Middlebrook approach. In this video, I will give two more examples of electronic feedback amplifier gain analysis. The first one will be a three-stage voltage sense voltage feedback amplifier, and the second one will be a two-stage current sense voltage feedback amplifier. We are now going to determine the voltage transfer function of this feedback amplifier, in which we sense the output voltage by a voltage divider and feed back that voltage to the input side, where it gets subtracted from the input voltage around this loop that we see here. The difference gets amplified through this first stage here, and then it gets amplified one more time through the second common emitter stage. We are going to use the low frequency model of the transistor that we've used before, the beta IB model. Here's then the equivalent circuit model of our feedback amplifier. In it, we can see the forward amplifying path this way from input to output, and the feedback path from the output back to the input. And even though we can see the amplifying path and the feedback path, we don't immediately see what are the G and H blocks in the feedback block diagram. And as I said, we don't need to worry about the G and H blocks separately. All you have to do is go into the forward amplifying path and recognize that if beta 2 were to become infinite, then the voltage gain from this node to that node becomes infinite. If, on the other hand, beta 1 were to go to infinity, then the voltage gain from this node to that node will not become infinite, only because the emitter here is connected to ground through some effective resistance. We don't need to know what it is, but we just know that there is some resistance between the emitter and ground. As for this stage here, it doesn't contribute anything by way of gain from the input signal to the output. So it is beta 2 that we designate as the gain element and apply the feedback formula given by the extra element theorem for beta 2. Up front, we have the ideal closed loop gain with beta 2 infinity, and we have the correction factor in which we have to determine the null inverse gain with respect to beta 2 and ordinary inverse gain with respect to beta 2. So first, let us determine the ideal closed loop gain, AVF, with beta 2 infinity, and we do that by letting beta 2 go to infinity on the circuit diagram. When that happens, beta 2 goes to infinity, IB2 will shrink to 0. Immediately you see that makes the voltage across R pi 2 and hence the voltage across RC both go to 0, and hence there will be no current in RC and there is no current in R pi 2, hence there is no collector current in the first stage, which means that beta 1 IB1 must be 0, which means that IB1 is 0. With IB1 0 and beta 1 IB1 0, the current in this branch here is 0, and if this current in this branch is 0, it means that also IB3 must be 0 because the sum of these two is equal to that current. So with IB3 0, the voltage drop across R pi 3 becomes 0. And what happens is that the input voltage V in gets copied across RB. Notice, if you look at this loop here, follow the dot, you look at that loop there, there is no drop across RS. IB1 is 0. There is no drop across R pi 1. IB1 is 0. Move on, there is no drop across R pi 3. IB3 is 0. And so V in gets copied over RB. When that happens, you realize that V in divided RB, which is the current through RB, is equal to the current through RA. There's no current here. So V in over RB is the same as V naught, the output voltage, divided by RA plus RB, the whole current here. And from this last one, you determine the ideal closed loop gain V out over V in as 1 plus RA over RB. And this reminds you of the gain of the non-inverting ideal operational amplifier circuit that you learned. So you don't need to have an ideal op-amp circuit to arrive at such a result. You can take your good old amplifier here, which is not ideal, and pretend that it is becoming ideal and get the ideal closed-loop gain. So we identified this portion here, and we need to identify next these two. Next, we determine the inverse gain with respect to beta 2 with the excitation set equal to 0. We replace here Vin with the short circuit, and we replace the dependent current source with an independent current source pointing in the opposite direction, and we determine the gain IB2 to IT. We're going to do this by successive current division of IT as we go around the loop back to IB2. Our first current division is between RL and RA in series with the parallel combination of RB with the reflected resistance into the base of Q3, which is R pi 3 plus the effective resistance in the emitter of Q3 multiplied by 1 plus beta 3. The effective resistance in the emitter of Q3 is nothing more than the resistance looking back into the emitter of Q1. And that one is Rs plus R pi 1 divided by 1 plus beta 1. We write all that down and we have R pi 3 plus 1 plus beta 3 plus times Rs plus R pi 1 divided by 1 plus beta 1. It follows that the current IB3 is first given by the current division of IT between RL and RA plus RB in parallel with this resistance. That gives us the current here in the resistor RA. That gives us this first current division. That current is divided between RB and the resistance looking into the base of Q3, and that one is given here, RB divided by RB plus this resistance that we determined, which is the resistance looking into the base of Q3. We could have also arrived at a similar result had we taken the Norton equivalent current source looking back from this node into this branch here, and the equivalent Norton resistance would have been RB in parallel with RA plus RL, and the equivalent Norton current source would have been IT times RL over RL plus RA, and that would have given us our current division into IB3. Once we have determined the current IB3, we can determine the collector current of Q1, which gets divided between RC and R pi 2 to yield IB2. Now, the collector current of Q1 is related to the emitter current of Q1 by the alpha 1 of the first stage, Q1. But the emitter current of Q1 is the same as the emitter current of Q3, which is 1 plus beta 3 times IB3. It follows that the signal current in the collector of Q1 is alpha 1 times 1 plus beta 3 IB3, which gets current divided between these two. And so now we have IB2 in terms of IB3. And in the previous slide, we had IB3 in terms of IT, which when we substitute in this expression, gives us the inverse gain of beta 2. We can simplify this expression if we let all the betas be nearly the same and all of them much larger than unity, so that alpha is unity, and we can ignore 1 with respect to beta and make all the betas the same, and we obtain a simpler expression for the inverse gain with respect to beta 2. Next, we determine the null inverse gain by replacing the dependent current source with an independent current source pointing in the opposite direction and determining the gain IB2 to IT with the response nulled. When the response V0 is nulled, then the current through RL will be 0, and the current IT that's coming down this way will flow entirely through RA, creating a voltage drop across RA given by IT times RA. However, that voltage will appear entirely across RB since the output voltage has been nulled to 0. That will start a current through RB given by ITRA divided by RB. That current plus IT will be the current IB3. And let's write that down. IB3 is IT plus ITRA divided by RB. Once I know the current in the base of Q3, I know its emitter current, and I also know the current in the collector of Q1. The current in the emitter of Q3 is 1 plus beta 3 IB3, and the current in the collector of Q1 is alpha 1 times 1 plus beta 3 IB3. And that current gets current divided between RC and R pi 2, and here it is. The current IB3 given by this expression here is multiplied by alpha 1 times 1 plus beta 3, which is the current in the collector of Q1, and that gets current divided between RC and R pi 2, and we can now get the null inverse gain by dividing out by eta, and that is the expression for the null inverse gain. We can approximate that for large beta by making alpha go to 1 and 1 plus beta just go to beta. And putting it all together, we obtain the closed loop gain of this feedback amplifier given by the feedback formula, in which the ideal closed loop gain is given by 1 plus RA over RB. The null inverse gain is given by this expression here, and the inverse gain with the excitation set equal to 0 is given by this expression. The gain, the closed loop gain, has been completely determined. The last example in the gain analysis of electronic feedback amplifiers is going to be that of a two-stage amplifier with current sensing and voltage feedback. In particular, we're going to analyze this current source here, in which we're going to determine the transconductance IDD divided by Vin. Notice what we're trying to do here. The drain current of M1, which is identical to the source current of M1, will flow almost entirely through RCS, since a negligible amount of it is going to be drawn by the amplifier. When that current flows through RCS, it will generate a voltage drop across it, which in turn is going to be subtracted from the input voltage, and the difference is going to be applied to the amplifying element, which will drive the gate of the MOSFET M1. Now, since RCS is going to be subtracted from Vin on this loop here, RCS has to be chosen such that the product IDD time RCS is comparable to Vin. So to analyze this circuit for the transconductance ID over Vin, we're going to be using the following models. For the amplifier, the op-amp, we're going to use this model here. And for the MOSFET, we're going to use this transconductance model. So the equivalent circuit model that we get when we substitute the model of the op-amp and the MOSFET is the one shown here. Once again, we can identify the forward path going this way to the output. The output is the drain current. And we can identify a feedback path. Now, in the forward path, we have two amplifying elements, A0 and GM. However, it is quite clear that if I let A0 go to infinity, then the voltage gain from the output to the input of the stage here is going to be infinite. Hence, A0 is going to be designated the amplifying element in the feedback formula for the transconductance ID over Vin. In it, GV infinity is going to be the ideal transconductance with A0 infinite, that is to say the op-amp as considered ideal, followed by a correction factor in which we are going to determine the null inverse gain with respect to A0 and the inverse gain with respect to A0 with the excitation set equal to 0. If we let A0 go to infinity, then the differential input voltage of the operational amplifier will go to 0. What that is going to do is that it's going to copy the input voltage across RCS, so that the current in RCS is going to be Vin over RCS, which is the output current ID. So now you see how you choose RCS. Typically, you choose it such that the desired current ID times RCS is comparable to your input voltage. So our ideal closed-loop transconductance is simply 1 over RCS. Next, we determine the null inverse gain with respect to A0 by replacing this dependent voltage source with an independent voltage source pointing in the opposite direction and nulling the response ID. With the current ID nulled, we determine the inverse gain V epsilon over Vt. We see that when ID equals to 0, Gm VGS is equal to 0. But since Gm is not 0, that means that VGS equals to 0. Hence, in the process of nulling the drain current ID, we are nulling the gate source voltage VGS. Now, when VGS equals to 0, Vt gets copied across RCS and it starts a current through it which will flow back into the amplifier's input and generate a voltage drop across Rin. That current is going to be Vt over RCS, so that the voltage across Rin minus V epsilon equals to Vt over RCS, this current, times Rin. And from this, the null inverse gain is computed as minus Rin over RCS. Next, we determine the inverse gain with respect to A0 with the excitation set equal to 0. We replace the dependent voltage source with an independent voltage source Vt pointing in the opposite direction, and we determine the gain V epsilon over Vt. In this circuit, we see that we have now Rin in parallel with RCS, and that GM-VGS is pumping current through their parallel combination and generating V epsilon, so that we can write GM-VGS times the parallel combination of RCS and Rin equals to minus V epsilon. We also see that going around from ground to this node here, the voltage is Vt plus VGS. Also going from ground to the same node, we have V epsilon, so that we have Vt plus VGS going this way equals to V epsilon going this way. And with these two equations, we can substitute for V epsilon up here and solve for V epsilon over Vt and obtain the inverse gain with respect to A0. Finally, we substitute the results we've obtained so far in the feedback formula given by the extra element theorem, and we obtain the expression of the transconductance of our current source. Up front, we have the ideal closed-loop transconductance, followed by the correction factor owing to the fact that the amplifier does not have infinite gain. Once again, we see that there's a negative sign appearing here, which means that one of the two paths from the input signal to the output must be inverting. The path through the amplifier, when the amplifier is functioning properly, is non-inverting, simply because if the input voltage increases, the current in this direction increases. It must be then, it is the path through the feedback connection that is the inverting path, and to see that, we just kill the gain of the amplifying path, and we determine what the gain is from the input signal to the output signal through the feedback path, while the amplifier is dead. Here we see that GM-VGS, since it is connected in parallel with RCS and talks to the voltage across itself, it acts simply like a conductance connected in parallel with RCS. And the input voltage is divided between RCS parallel 1/GM and Rin. And that pushes a little bit of current in GM in the opposite direction. And that is what accounts for this negative sign that we see here. Well, that concludes gain analysis of electronic amplifiers. And for more examples, please refer to my book.